Good morning, everyone. Okay, today we're going to keep doing work, but we're going to take a different type of work problems. So this is the problems that we're going to look at. I will read it and then we work on it. So work done in pumping liquid from a tank. Okay, we're going to consider the following problem. A cylindrical tank of radius 4 feet and height 10 is filled with water to a height of 8 feet. The question is, so we have water and we're going to lift them. So find the work required to empty the tank by pumping all the water to the top of the tank. And the density of water is given to you, 62.4 pounds per feet cube. Okay, I'm just giving you time to write this down.
Can you scroll up a little bit?
Or down.
Or down. Thank you.
Okay, let me know when you're done so we can start. Okay. Are we ready? So what is it we have in this problem and how does this scenario changes from the scenario we've seen about work? Okay. What we have seen about work so far is the following scenario. Basically, we have a specific object, so an object, whatever, and we're moving this object. But as we move this object, the force we need to move it was changing. That's really our scenario. And so it's a very specific. We're holding this object basically and we're moving it. So in case of the spring, we actually have the end of the spring, which is that's my object, and we're moving the end of the spring. And as you move it, the force we need changes. So we had f of x here, the force need to move the object a little bit. And then we find that the work needed to go from a point A to a point B is the integral from A to B of f of x dx. That we've seen so far. But in this problem, the situation is as follows. So we have the cylinder. That's really what the problem is. We have a cylinder. And the cylinder is filled with water. So we have a whole body of water in here. And we want to lift all this water up. So we're going to lift everything here. So it means every drop of water, whether it's here or here, is going to be lifted. So we're not moving only one object. We're lifting a whole body of things. And the issue we face here that we did not face in the previous problem is that the water at the top, if you take a drop of water here and a drop of water here to lift it, the work is different, very different. It's not one object I am moving. So if I want, and this is 10 feet, so it's really a long, it's a tall cylinder. So if I want to lift this and this, the work changes. Why the work changes quickly? Why the work changes?
Is it because we're adding height to it?
Right, the distance by which it's lifted is very different, right? The distance, remember, this is 10 feet from the bottom to the top. To lift this drop of water versus lifting this, the work is really, really different. This one, I'm going to move it from here to here only. And this one, I'm lifting it from the bottom of the cylinder all the way up. So while this, I may lift it like 2 feet or 3 feet, I have to lift this almost 10 feet. So the work done is very different between this drop and this drop. So I cannot really use this scenario. I don't have one specific object. I am moving. So things are very, very different in this idea. So how are we going to solve this problem? How are we going to find the work? And I'll show you the idea, and then we do the work. The idea is we have this problem of distance between those two drops. So what we're going to do is what we do in those problems. We're going to break the water inside the cylinder into layers, basically very, very thin layers, so that all the water within the same layer get lifted by the same distance. And that's going to be our strategy. So we're going to divide the water inside here into layers, so that the water within a layer, very thin layers, will be all lifted by the same amount within the same layers. And then we're going to add the work done on each layer and find the work. So before we do that, how am I going to divide the water in the cylinder into layers so that water within the same layer get lifted by the same amount? How shall I do that? I'm going to really split it into pieces so I can basically control the problem, control one aspect of the problem. How shall I divide it? How shall I do the division?
In like discs?
Yeah, horizontally or vertically. Let's talk about that.
Horizontally.
Horizontally, because the idea is I'm gonna divide it into pieces horizontally. Like this is a piece. If my layer is very, very tiny, the water within this whole piece will be lifted by the same amount. That's really gonna be the logic. And then I'm gonna top it onto another layer. So of course, those are going to be very thin, not like the picture. And then another layer. Let me change color a tiny bit. Again, the layers has to be very thin. So that's another layer. And then a top layer. We're going to, of course, divide into tons of layers. And this layer. And then the way we're going to think, okay, to lift those, the total work is the work to lift this. So when I see how much it needed to lift this piece, we're done with it. Add to it how much we need to lift that piece. That's how we're going to think about it. We're done. Add to it how much we need to lift this piece. Add to it how much we lift that piece. So we're going to do the problem, work on this, plus the work we need to lift this, plus the work we need to lift this, plus the work we need to lift that. So in the picture, of course, I only have 4 layers, but in reality, we're going to divide into lots of layers and layers in general. And the goal is, if the layer is very thin, this from here to here is so tiny that the water within this whole layer will be lifted by the same amount. So that's really the logic of what we're going to do. So we're going to divide the water within this into layers, find the work done on each one of them, and add the work. So that's really the strategy that we're going to do. And we had forced to do the strategy because I don't have force. If you tell me f of x, I don't know what f of x mean in this scenario because I don't have a specific object I'm moving. I have a whole body of water. So there is no concept of f of x in this particular problem. All right, so let's get to work. And this is really idea. So the idea is, let's start doing the problem. So this is my cylinder. I draw it again. That I'm going to work with it. So this is my cylinder. Okay. And there is water in it, and the water is up to 8 feet, up to here. And this is 10 from here to here. So that's my picture now. And the radius of my cylinder is 4 feet. Okay. So what we're going to do is, as I said, we're going to divide the water within layer. But now how we are going to divide this water into layers? So we're going to take an axis. So we're going to pick a point here to be the origin, and I'm going to pick an axis, going to call it the y-axis. I will go pick it going up. Okay, so I'm going to create a certain reference. 0, I'm going to call it the base of the cylinder, and I'm going to go up the direction of, actually, it doesn't matter how you're going to go, whether up or down, but we're going to choose to go up as my positive direction. And then I'm going to divide. So we're going to, the way we do those problems, we're going to divide the interval. And there is water up to 8. So up to that, after that, there is no water. So I'm interested in dividing the interval from 0 to 8, not to 10, because there is water up to 8. So we're going to divide the interval 0, 8 into n equals subinterval. Of length delta y. So very, very tiny pieces. Okay, so we're going to divide 0, 8 into n equals subinterval of length delta y. And we're going to use those subdivision to basically divide the water in the layer, and this will divide, actually, and we use those subdivision. To divide the water in the tank into horizontal layers. Okay, so I read. So we divide the interval 0, 8 into n equals subinterval of length delta y, and we use those subdivisions to divide the water in the tank into horizontal layer of height delta y each. Okay. That's what we're going to do. So let me go back to the picture, and the rest will be actually not very hard. Okay, let me go back to the picture. What we're going to do is divide this as I did previously, here. That's really the picture I want you to have in your mind. That's exactly what I'm doing. So I'm going to divide this into layers. So let me take this subdivision. Suppose this is yi. It doesn't have to be in the middle. It's not in the bottom. It's not in the top. It's somewhere there. So this is my yi, and I'm going to do my subdivision. So this is my layer here. My little disk. It's going to be a disk, my layer. So that's the delta y, which is very, very tiny. And this is a typical layer. That's really my layer. In your mind, I'm dividing the whole tank into layers, but I will concentrate on one of them. Okay. Now, a typical layer, that's what we always do, a typical layer in this particular problem is a cylinder or a disk, because delta y is going to be very small, is a disk that is yi feet above 0 and with height delta y. So that's really my typical layer. It's a little disk. That's yi feet above 0 with height delta y. Now, what we're going to do is we're going to just focus on one layer, and we are going to find the work needed to lift a typical layer. So work, and sometimes this is called the element of work. The work needed to lift a typical layer. Is equal to okay. So a typical layer. What does the work need to lift a typical layer? All right, anybody can tell me. At this stage, we should be able to work the whole problem together. So now focus on one piece. That is yi above the ground. So this is my yi here. And this is my 0. I have this piece right here. What's the work needed to lift this piece? So we're gonna imagine now we have a bunch of pieces. I focus on one of them and I wanna lift this. What's the work I need to lift this piece? Forget about the water above, forget about it below, focus on that. What's the work needed to lift this particular piece? Anybody can have any idea. And then
Maybe force times distance.
force times distance. Force, what's the force in this case? So focus on this one. That's what you're lifting. Forget about water above, water below. That's particular layer. This is, I draw it again. That's what I am lifting. So what's the force to lift this? Remember, there is water inside. What's the force to lift this? And I'm going to lift this all the way to the top. So this is going to be lifted all the way to the top of the tank. All the way to the top of the tank. That's what I'm focusing on. Okay, force times distance, you're absolutely correct. All right, let's write this down. So the work is the distance by which a layer is lifted, distance by which layer is lifted, multiply it by the force needed to lift the layer. Needed to lift layer. Now I'm going to take each piece by itself and focus on it. What's the distance by itself and what's the force? And then we multiply them. So let me ask the first question. What's the distance by which a layer is lifted?
8.
When I don't say yes, it means
The Y.
no. Go back to your picture.
Is it
Always
10
use the
minus
picture.
Y?
All of you. This is my layer. I want to lift it all the way to the top. This is my 0 down here. The layer is YI unit above 0. Means from here to here in your mind, there is YI feet. What's the distance?
10 minus yi.
8 minus y.
8 minus yi.
Make up your mind.
8 minus yi.
That's what I'm saying. That's what I think.
At 8. Anybody would disagree? The height of the cylinder is how much?
10.
10. Very good. It's filled with water up to 8. And we're going to lift it to the top of the cylinder. That's why sometimes we have to read the problem. We're going to lift this to the top of the cylinder. Okay, not up to here. We're going to lift we're going to pump all the water to the top of the cylinder. So if I focus on this layer, if I want to pump it to the top of the cylinder, by what distance I'm going to do it? Yes, Kiana. Now it's going to be 10 minus the yi, because I'm going to lift it all the way to here. So it's not 8. 8 will lift it to the top of where the water ends, but we have to lift it all the way to the top of the cylinder. So we're going to lift it by 10 minus the yi. That's my 0. So my yi in this particular problem is from the base of the cylinder up to where my layer is. So the distance is going to be 10 minus yi. Do you understand why it's 10, not 8?
Yeah, that makes sense.
Everybody, I want all of you to follow me. Now, part 2 is, so I took care of the first piece. Part 2 is force needed to lift a layer. Okay, it says a layer, we have to lift it. What's the force I need to lift the layer? So let's pick up another piece of paper here and focus on the force. All right, force to lift a layer. Is this layer. I wanted to focus on this one. So for you, that's the object that you are moving to lift a layer. Okay, what's the force? Back to you. Oops. Think of this layer as an object that you want to lift it. What's the force you need to lift a particular object? And for us now, the force is constant. So what's going to be the force? Don't be afraid. It's not hard, the force. It's the weight of the water inside the layer. Inside the layer. Okay, so the force you need to lift a layer is nothing more than the weight of the water inside this layer. And now let's see what's the weight equal to. So this is imagine you have a cylinder, and this little cylinder from here to here, it's a delta Y, is filled with water. The weight is the volume of the water, the volume of the cylinder times the density of the water. Okay, so the water has a density, so the density is 62 pound per feet cube. Okay, so the weight is going to be the density of the water times the volume of the cylinder. Okay, because what's density? The density is the weight per feet cube. So to get the weight, so this is nothing more than density of water. So the first problem, as usual, I write it in a lot of details. So it's the density of the water times the volume of the disk or of the layer of the disk. Now, the density of water, I gave it to you. It's 62 point, I don't know what number, 60.5 or 4, 62.4. That's nothing, the density. Now, what's the volume of the disk? Back to you. Yeah, what's the volume of the disk? Look at it carefully. What's going to be the volume?
Pi r squared times h.
Pi r squared. What's r squared in this problem?
4.
4.
And then
Times, exactly. What's the h in this problem?
the 10 minus yi.
No.
Delta y?
Delta y. Why delta y?
Because you're looking for the height of an individual layer.
Exactly. I'm looking for the height for the individual layer. That's the piece. Otherwise, I'm not looking for all the water because I'm back into the same issue. The distance to lift this, the distance to lift this, it will be very, very different. That's why I'm focusing on a layer, because if delta y is very small, whether the drop of the layer in drop of the water in the top of this layer or right here, if delta y is very small, the distance by which this and this are lifted is almost the same. It's going to be 10 minus yi. I'm looking at the individual layer. That's really my delta y staring at me right there. So that's the weight of, that's the force needed to lift a particular layer. So now finally, I'll put the whole thing together. So work to lift layer, one particular layer. To lift a typical layer is the distance, which was 10 minus yi, times the force, times pi, times 16, which is the radius square, times delta y. Okay, so the delta y is actually part of the force to lift a typical layer. So the total work is the sum of the work done on each layer. Is almost equal to the sum of work done on each layer. So at this stage, I am back to my original picture on each layer. Okay, so now I am back to this scenario. The total work is the work to lift this, plus the work, plus the work, plus the work. That's really how I am thinking at this stage. That's where my Riemann sum will come from. So which it means equal to sigma of the 10 minus yi times 62.4 times pi times 4 squared times the delta y equal 1 to n, 0 to n minus 1. This really doesn't matter at this stage. So now, as delta y become very, very small, and that's crucial in this case, it means as the number of subdivision gets very large, so delta y is very tiny, my approximation gets better and better because in this case, within the same layer, the water within the same layer is lifted by the same amount. So my approximation of the distance become a very good approximation. So now approximation gets better when delta y become very small. So now this is going to give me the work. So this is a Riemann sum that we're going to transform it into an integral. And the integral is 10 minus y, 62.4 times pi times 4 squared dy. And the last piece in any integral, we're computing a quantity now, is to find my limit of integration. And what are the limit of integration in this particular problem?
Wouldn't it be 8 to 0 or 0 to 8?
Exactly, it's going to be 0 to 8. So usually whenever we want to find the interval of integration, we go back to our problem and we ask ourselves which interval we had to cut into pieces to cover all the water in my layer. There is water up to 8. So we have to divide the interval from 0 to 8. So that's integral from 0 to 8 is always limit of that. Okay. And now the rest is actually doing math. So the first step, I get all my constant out. So I will have 62.4 times pi times 16 integral from 0 to 8 of 10 minus y dy. Okay. And then the rest is really nothing more than, doing the simple math. So we have to find the antiderivative and then proceed. So this is going to be equal to a bunch of stuff. If you multiply this by this, I don't need to, but I do. I think I get that much. And then that's the piece. So between 0 and 8, when I get 10y, antiderivative, minus a half y squared. And this is 8. This is 8. This is 8. And this is going to give me equal to, I'll write it here. It's 998.4 pi times. At the upper limit, I'll get in 80 minus at the lower limit, I will have 64 over 2 minus 32. Give and take a stupid mistake. And then I multiply this whole thing and I got the following number. And my unit was pound foot. Okay. So that's how we are going to deal with those problems. Now the book is giving.
Could you tell me, could you say the label again? I couldn't hear that. And I can't really see it on the
What?
the screen.
I didn't understand.
Just the label.
Label. What do you mean?
Like
unit?
Yeah, the
Unit.
unit.
Unit, yeah, pound foot. Because
right,
this is the unit that they are given to us. It depends whatever the unit the problem gives you. Okay.
All right, thank you.
All right. The book is giving you a formula, and I don't want you to use the formula. I want you to do it exactly the way we're doing it in class, because this helps you understand what we are really doing instead of memorizing a formula that I don't even memorize it. I don't know what it is. Okay, so I want you to handle it this way. For that reason, I will put my notes also on right space to help you out. Okay, now we're going to take another problem. I mean, that's the only idea we're going to work on today. And we're going to do it. So I will put the problem. So what we're going to do now is basically changing, not the concept, changing the shape of the tank in which we have water. And changing the shape does not change the concept in which we are going to work. It's change a little bit the algebra, basically, and the geometry. Will not change the way we're going to do it conceptually. So this is my second problem. Okay. So we have a tank. I changed the shape of it, and it has the shape of a cone with height 10 meters and radius 4 meters. And the tank is filled with water to the top. Find the work required to pump the water out of a spout 2 meters above the top of the cone. I will draw the picture to make the cone well understood. The density of water is 1,000 kilograms per meter cube. And remember, kilograms is a unit of mass, not a unit of weight. So I'll let you write, and then I'll draw the picture, and we go from there. Okay, ready? Okay, are you guys, can I move on? Yes or no?
Yes.
Everybody?
Yes.
Okay. Okay. So the idea here is it's the same picture. I want to have a paper from the top. That's really my picture here. I have a cone, you know, this cone, I'm gonna draw it with like this. I could have drawn it other way, but I'm gonna take this problem. This is my cone. And this cone is filled with water all the way to the top. And there is a spout. We're gonna pump the water from a spout, which is 2 meters. So this my spout go like this. This is 2 meters here. Okay, and I want to drop the water from here. That's the picture. The dimension of the cone are the height of my cone from here to here. It's, so did I give you 10 meters? So my units are meter here. And the radius of my cone is from here to here, 4 meters. Okay. And from here to here, so the spout from which we're pumping is not at the top, is 2 meters above the top of it. So that's really the dimensions we have. And my problem is we have to pump all this water. So I am in the same situation. I have a body of water to lift. So drops here will totally be moved by the different distance. I'm gonna divide into layers and focus on each layer by itself. Okay. To do that, we have to introduce a reference to work with. So I'm gonna, as like I did in the previous problem, I'm gonna pick 0 down here, and I'm gonna take, so right in the middle, and then take my y-axis. So this is my y-axis going all the way to the top. That's my y-axis. I'm gonna do it in the direction of motion. This is my y, okay? And then I will do verbatim what we did in the previous problem, absolutely verbatim. What do I mean verbatim? It means I'm going to divide this water into layers. The layers are changing here, and I focus on each layer and find the work needed to lift every layer. Now, of course, we're not gonna do each one by itself, so we take what we call the typical layer, we find the work on it, which gives me the formula for the work on each one of the others, and then we add. So let me focus on the layer. All right, so we need to find the work done on a typical layer. And what do I mean by typical layer? It means a layer. It means a layer which is yi feet above the base with height delta y. With height the delta y. So I'm going to draw this. So this is yi. And as I said, I don't want you to draw the layer at the bottom. You get confused. Or at the top. You draw it somewhere, not necessarily halfway, but somewhere in between. So this is my yi right here. This is my yi, and that's my layer here. Okay, that's my layer. So you imagine you're cutting horizontally. That's what you have to imagine. You have this cone, and you are cutting it horizontally by layers. And this is really my layer right here. That's the layer. And that's what I'm going to focus on. That's really my focus. I forget about the water everywhere. This is the only layer. That's this little piece that I need to focus on. So this is my delta 1. Okay. So work done on each layer, exactly like the previous one, is the force by which, sorry, the distance by which we need to lift it times the force. So work done on a layer is the distance by which a layer, the distance by which a layer is lifted times the weight of the layer. Times the weight of the layer. The force by which we need to lift it, which is the weight in this particular problem, the weight of the layer. Now we're going to do each one of them separately. First, the distance. Okay, back to you. What's the distance by which a layer is lifted?
12 minus yi.
12 minus yi. Do you agree with him?
Yeah.
Do you agree? Because it's going to be lifted from here all the way to, because the water is not going to be lifted to the top of the cylinder, the cone is going to be lifted to the spout. So it's going to be lifted from here all the way here. And from here all the way here, this is 12 minus yi, because I have to add those 2 meters for the spout. So the distance is 12 minus yi. The distance is not hard. Okay, now the weight. The weight of a layer. One layer. Remember, I'm focusing weight of a layer. Okay. Again, the weight is the density times the volume. Density of the water times the volume of a layer. Okay. So now let's see what's the density. I gave you for density this time, I gave you 1,000. But the unit was the kilogram per meter cube. Okay. But if I take 1,000 times the volume, my unit will be kilogram. So to be able to get a unit of weight, I need to multiply by 9.8. Okay, that's something we did last time. If I only put 1,000 for density, that's kilogram per meter cube. It means how many kilogram per meter cube. Multiplied by the volume, it only gives me the unit in kilograms. So I have to multiply by 9.8 to get basically Newton per meter cube, which is gonna give me unit of weight. Now, what's the volume of the layer? Go back to the picture. And how this problem is gonna change from the previous problem. Is the weight of the layer gonna change with its height above the base in this problem? Okay, if I go back to this original problem here, to my first problem, when it's a cylinder, what was the volume of every layer? It's pi times the radius squared times delta 1. In this problem, the radius was the same regardless where I take the layers. So the radius of the layer did not really depend on where I am within the cylinder. It was absolutely constant. So that was 4, 4, 4, regardless where my layer is. What about in this scenario? Is the radius of the layer gonna change with the height above the ground? Yes or no, quickly?
Yes.
Absolutely. So this is R. So now to find the volume of the layer, I have an issue. That's Ri, and Ri is changing with where I am on the layer. So to lift a layer at the bottom, actually, it's going to be a lot more work than to lift a layer up for two reasons. First, more distance. Second, it's heavier because the radius is much bigger. So now I have an issue. So the volume of the layer is going to be basically pi times the radius, which is changing this time because each layer is a disk, times the delta y. So now my question is, I need to be able to do this problem. I need to find a formula for the radius. And y is my only variable here. So I need to express the radius in terms of y. So we need to find the radius in terms of y because we have to find everything in terms of my variable y. So how can I find the radius? So we need to find, oh, this isn't, I need something darker. So we need to find Ri in terms of yi, because that's the only thing in this problem that I wanted to vary. I cannot have two different variables. I cannot integrate. So how can I find the radius in terms of the height? I keep the picture in front of you. So I want to see yi is from the base to here. This is my radius. And I need to find the radius in terms of yi. So to help us focus, I'm going to take this rectangle, which is sitting right. If you take a vertical slice and you cut the cone right in the middle, you're going to get this rectangle. So this is the rectangle in the middle. I'm going to take it here and I'm going to reproduce it to help us figure out the relationship. So this is my 4 because that's the radius at the base. And this is my 10 up here. So this is the rectangle. I'm trying to write it here. And this is my yi. It means from here to here. This is my yi. So we have to know exactly what my yi is. And from here to here, I have a 10. And this is my radius here. Okay. And now I need to express the radius in terms of yi. Is this a hard problem or an easy problem? Back to you.
I think it's easy. Can you just set it up as like a ratio almost?
Absolutely. Absolutely. We're going to set it up as a ratio. I don't have really other choices. So we're going to set it up as a ratio using the idea of similar triangle. I mean, there are two ways, but the one easy way is set up as a ratio. I said this small triangle, let me give it a name, A, B, C. And the bigger one, let me give it, this is O, I cannot change it. And let me call this D. So the triangle ABC is similar to the triangle AOD. So we have to, it means that the ratio between the side is the same, okay? Let me use my picture here to set up the, remember I need the relationship between R, the radius, and Y. So that's really what I'm going to be focused on. So I'm gonna say that the ratio between this side and this side, which is 4, okay, is equal to the ratio between from here to here over 10. That's the ratio I'm setting up. Okay, so it's going to be equal to, this is my 10 down here. And from A to B, how much do we have? Again, you look at your picture.
10 minus y.
10 minus YR. Okay. And this is going to give me the radius is 4/10. That's 10 minus YI, or 2/10. I mean 2/5, 10 minus YI. And that will give me the radius in terms of YI, because it's changing. It's not constant like the cylinder. So it's slightly harder than before. So the principle is the same. What's going to change is the shape of the tank that we are going to be working with. Okay. So now let me put the whole problem together and we will be done with that. So it is equal to, okay, 1000 times 9.8, that's going to give me times. And let us fill up the rest. Times pi, I'm still working on a layer. Now the radius of a layer,
Wait, you said 1000 times 9.8. Wouldn't
yes.
that be 9800?
Of course, it's too early for the morning. Okay, what's the radius? Sorry, 2/5, 10 minus y. Okay, so now work done on a layer. Work done on a layer is almost equal to the distance by which a layer is lifted times the weight. Delta y. And that's 2/5, 10 minus y. Okay, that's the work done on each layer. Now what we have to do is add the work. That's really our idea. So we find work on each layer and then we add the work. So now work is almost equal to the sum work done on each layer. Okay. And as I said, in physics, sometimes the work done on each layer, they give it a name and they call it the element of work. Okay. That's the little bit of work. And then we add those little bit. So this is nothing more than the sum of the 12 minus yi times the 9800 pi times the radius. Delta y. So finally, the total work. As we know, when delta y become very, very small, my approximation is better because I can assume the water within a layer is lifted by the same amount. If delta y is big, then this is really nonsense. So it's going to be the integral of 12 minus y times 9800 pi times 4/25. That's my radius, then minus y squared dy. The last piece, as usual, we have to figure out our limit of integration. Okay. And to do that, we go back to the initial picture and we ask ourselves, what did we have to divide into pieces to cover all the water inside the tank? And I take you back to the picture. What are the limit of integration?
0 to 10.
0 to 10, absolutely, because it was filled up to here. So my limit has to be from 0 to 10. So integral from 0, that's the bottom limit, up to 10, that's my upper limit. Now the rest of the integration, I don't think it's hard. First, we take those out of my integral. Times pi/25. And then I will be left with the integral from 0 to 10 of this quantity up down here. And the only way to integrate this piece is by distributing and then integrating. Okay, so the only way you can do it is distribute and then find the antiderivative. So you're gonna get a number, and this will have to be in joule because that's usually our unit. We took the kilogram per meter cube, we multiplied it by 9.8. Doing that will make the unit Newton per meter cube. That's the unit of the force, and the measurement were in meter, so the unit of the whole thing is in joule. Okay. Okay. All right, so for tomorrow, I want you to do the homework. Some of them are a little bit harder than others, but as usual, you guys give them a shot, and we will talk about them tomorrow. Okay, they are already on MATLAB. Any questions before we finish the section? Any questions? Okay, so I'll see you tomorrow then. Bye bye, guys.
Thank you.
Have a good one.